Right then. All right. Well, thank you, Dula, and thanks to everybody for joining us. It's afternoon over there, but it's nice and early in the morning here. Still dark and lots of snow. Anyway, we're going to go here today and talk about the quad neutron and share some insights with the technology and show some case study examples for you guys. So, and as Adula said, questions, I'll pause at sections in the presentation where we can address questions. Anyway, so the objective is to learn more about quad neutron technology, currently being available in Nigeria through BOAS. We're going to introduce a little bit about Roke because most of you guys don't know who Roke is. We'll do an overview of the technology, and then we'll show some international case studies, and then we'll do some specific Niger Delta case studies. And then we'll talk briefly about some new developments for working here at Roke that might be of interest. So, quick history on Roke. We've been around since 1967, primarily started in the coal mining industry. The company was started by an ex-Schlumberger R&D engineer. In 72, they started formal research for the quad neutron. And in 83, the tool actually was built and entered the market. This picture down in the corner here, this is 1967 coal mining in Canada. So I can tell by the vintage of the truck. Roke today, we do everything here at Roke. This is our headquarters. We're headquartered in Calgary, Alberta. So we are focused on oil and gas technology, no longer with the mining sector. We focus on through pipe data technologies. We have our own commercial products. We do our own development here. We do training, R&D. We even write our own software. If we look at our pipeline of oil and gas technology, we have a number of different technologies we work on and that we've developed. But for today, I'm going to focus on quad neutron. Before I jump to talking about it, we are also in the development of a spectral quad neutron tool, and I'll talk about that near the end of the presentation. So worldwide, this is where we sit worldwide with quad neutron tools that have been run. And also where we have pending agreements, we've got tools being shipped to these light blue countries or have pending agreements that are waiting on tools. So before I dive into the quad neutron, I just really want to highlight for those of you guys that have experience with logging tools, with pulse neutron, with open hole tools, and what makes the quad neutron unique? Well, the unique features of the quad, it's a dual physics measurement. And hopefully by the time we get to the end of this presentation, you understand what I'm talking about in that regard. But we combine a neutron, and neutron gamma measurements. We combine them. And the other unique feature is that the source does not activate pipe. It's a chemical neutron source, but in through pipe measurements, most people use generators, or minitrons, and those activate iron easily. Ours does not, so that gives us some advantages. The tool can be run in memory or real time, and it's a robust, slim design. We've used the tool in logging well drilling application. So with those unique features, we get some interesting benefits. We get a deeper depth of investigation than other tools. Because we use dual physics and we can combine mathematics, we can use the tool in a standalone mode. So we don't need open hole data to do an interpretation. We can provide some relative density and some clay or dolomite volumes with our tool. And because we do not activate pipe, we can use it. We can log using pipe, and we can also do logging through multiple strings of pipe more because we have the deeper depth of investigation. Okay, so anyway, here's a quick summary slide of the quad neutron. It's not very interesting to look at. It's a slim tool. It's 1/11/16 diameter. Depending on its configuration, if it's in E-line, it's 4.8 meters long or 16 feet long, and if it's in memory, it's 7.4 or 24 foot long. It's 150 degree rated, 150 degree C rated. Standard ratings is for any downhole tool for the most part. Like I said, it's a dual physics measurement. So what do I mean by that? So the tool is configured with the source in between two physics. And so we have neutron gamma detectors above the source, and we have neutron detectors below the source. And we combine the readings from these four detectors and do the mathematics. And hopefully I can make that clear as we go through the presentation. We provide saturation, porosity, lithology, and a qualitative permeability measurement. We can identify and differentiate between oil, water, and gas, no issues there, and through multiple strings of pipe. Applications, bypass pay, reservoir monitoring, production completion optimizations, water shutoff, new drill evaluations. We use it for a number of different applications. And as I mentioned before, we can run it standalone. So this is handy for people if you have troubles getting open hole data. It's an option. If you've got old wells, we do a lot of old wells for people where there's no data available. It's a robust, slim design, so we can go everywhere with it, and seems to withstand a lot of punishment. And it is the deepest reading through pipe device in the market. So I'll talk about that here. So depth of investigation for Neutron devices, the depth of investigation is defined as where 90% of the count rates have been accounted for. And if you read any of the textbooks on it, they talk about that the depth of investigation of the far detector, that's the detector farthest from the source, is the deepest reading detector. But when you actually look at it by taking the ratio, you actually cancel out the common component of the measurement, and it actually just looks at what's remaining. And there's good books on it. I don't know if you guys have had a chance to read this book, but Well Logging for Scientists, excellent textbook. This is an old version I had, but it talks about depth of investigation on neutron devices. So here is a quad neutron response chart. It's a pain. This is, I don't know if I can like this. So we do Monte Carlo modeling on the tool. And when we model this scenario with 15% porosity, a freshwater filled sandstone, these are the depths of the count rates, and it's integrated as a percentage. So what I'll show here is the first four, SNN and LNN, that's the short neutron and long neutron, and SNG and LNG, that's short neutron gamma, long neutron gamma. So if we look at the short detectors, the short neutron gamma and short neutron, one of the things that we tried to accomplish with the design of the tool is to make sure that the two physics are matched spatially when they do the measurement. And you can see when we look at the integrated response that both the short neutron and short neutron gamma are very similar in their depths of investigation. That allows you to do math without worrying about not comparing the same hole or measurement volume. But if we take 90% for these two detectors, the short detectors, you can see it crosses about here, which is about 300. So 340 for short neutron gamma and 330 millimeters for the short neutron. If we now look at the long neutron and long neutron gamma, they cross the 90% threshold here, just over 400. So 419 for long neutron and 429 for the long neutron gamma. Now, if you take the ratio of each of those physics, so if you take a neutron ratio and you take a neutron gamma ratio, which the neutron ratio is DDN and the gamma ratio is DDG, it's these blue and orange curves here. You can see that they cross the 90% threshold a little deeper at 500 millimeters. Again, that's just as per the textbook. It's bang on. It's exactly what it does. Now, in the quad, because we use two physics and we use two detectors for each physics, we're able to do 4 detector mathematics. And 2 of our primary curves, which I'll talk about in better detail coming up, is QTP or quad total porosity and our QL or quad liquid curve. So these are 4 detector mathematics. And so when you look at how deep do these two curves, and these are the two curves that we look at saturation, and we do a number of different measurements for the formation with these curves. Here's the response function of them, and they cross at 90% here. So mathematically, we're able to actually read deeper with the quad neutron. So in this example here, they cross at 691. People always ask, what's the depth of investigation of your tool? And they want a single number because that's what they've been taught their whole life. But quite honestly, you need to know the environment. The environment dictates the depth of investigation. So I'll show you an example of that. So same 15% porosity sandstone, but this time we put methane in it. So if you look at just our QTP and quad liquid, we're out at 930 millimeters. It's the same tool. The only reason it reads deeper is because the environment allows it to. It's more neutron friendly, neutron gamma friendly environment. So depth of investigation is related to the environment. Another unique feature of the quad neutron, I'm just going to hit these little highlights here, is that we exploit the thermal neutron nuclides, which is elements that actually get activated by thermal neutron capture, and they emit gammas. So that's what a thermal neutron nuclide. And so when you look at these elements, aluminum 27, which is 100% in nature, there is no other isotope of aluminum. So there's 100%. When it captures a thermal neutron, it actually goes to aluminum 28, which is an unstable isotope. And to decay to stable state, it emits gamma radiation. So in this research done, here's a reference to it, it's emitting 27,000 counts per second per gram of aluminum. And so when you look at the table of values, chlorine 37 is a thermal neutron nuclide, but it only exists in nature at 24. So when you look at this table, we're very sensitive to aluminum. In carbonate, full neutron nuclide, and that's magnesium. So we can actually exploit that for dolomite volumes. But exploiting aluminum, this feature of aluminum, we can do a clay estimation. And so here's an example of some clay data. I'll just show you this. And to show you our clay calculation, this shading here, this red curve here is our clay measurement. And it's based on that thermal neutron nuclide. The dots here in this core were taken from core. But I want to bring to your attention the gamma ray. So in this formation, this is the Montney formation. The upper formation is very radioactive. It has a lot of gamma activity. So if you did a V-shale gamma ray, you would be misled in the actual clay volume that you're, or the shale volume, to be honest with you. It's just radiation driving the gamma ray. But our clay measurement was not tricked by the radiation from the shales, from the gamma. And in the lower part where the gamma ray is less, the clay volume is actually higher. So that's how we can use that. It gives us some advantages when you're doing formation evaluation, looking at your lithology and the amount of clay present. Another unique feature by having dual physics measurement is doing a relative bulk density. And so the measurement, we call it our CE curve. But at the end of the day, what we do is we actually look at, we normalize our neutron counts versus our gamma counts. We know that if we have 1,000 neutrons, for example, we should see a certain amount of gamma rays. So if we normalize, let's say 1,000 neutron counts to 1,000 gamma, and then we continue looking at our interpretation in the wellbore, if we still have 1,000 neutrons, but now we only have 800 gamma, that to us is a flag, and it also indicates that there's an increase in density because there is only one unique physical property that will change the gamma counts if we still maintain the same neutron counts, and that's an increase in density. And vice versa, if we have 1,000 neutrons and now we have 1,200 gamma, that means we've decreased in density relative to where we've normalized. And I'll show you guys some examples where how we exploit that and what information we can get out of it. Here's just a quick example. To be honest with you, I wish we were all brilliant and say, oh, we knew that would happen. But quite honestly, it was this core data set. This is 270 meters of core. And the blue dots, the blue curve is our density calculation. The black is actually the core, and the red was the bulk density from open hole. It wasn't until we actually had this data set that we truly appreciated that we were measuring density. So I wish, like I said, wish we could say we were brilliant. We knew that ahead of time, but this is some of the insights we've learned over the years. So I'm going to pause here for a second. I'm going to dive into quad principles. Are there any questions at this point? Feel like I'm having an AGM. Hearing none, we'll proceed. Okay, I'll go through the quad principle. Maybe that'll drive some questions in. So what is the principle behind the quad neutron measurement? So the principle is called porosity liquid error. We did a paper in this in the 80s on it. It's still not very well understood, but I'll do my best here trying to explain it. So all logs are calibrated using fresh water. This is standard for open hole methodologies. And so matrix changes affecting porosity have been studied to exhaustive lengths, but fluid changes affecting porosity has not. So fluid changes in uniform reservoir can cause up to 35% porosity error in some logs. So what am I talking about, this fluid change causing porosity error? So let's so I'm going to do a very simple. If we have a bucket reservoir 30 full of sand, it's 30% porosity in that bucket and it's full of fresh water. What happens to logs when the reservoir fluid changes and the matrix stays constant? So for example, in my little bucket, if I have 70% sand and 30% fresh water, that makes up our 100% volume in the reservoir. Here are the densities of these. Now the density of the liquid, this is the electron bulk density, because we're going to look at what the density tool measures. When you calculate that, here's the density of this bucket. If you do the porosity based on a density log, you come up with 30%. That's what it's calibrated for. Hallelujah, everybody's happy. That's what we wanted, 30% porosity. If we now put oil in the bucket, still maintain 30% porosity with a 70% volume, we actually get 32.7% porosity, but the porosity never changed. It is still 30% porosity in the bucket. So this is an example of porosity error. If you look at a table of different technologies and different measurements out there, and you go from a 200,000 water to a 40 API oil, here's sort of the range of errors that you can see. So as you go down the list, if you were to look at total porosity error, epithermal neutron has a very low porosity error. Neutron gamma, if you look at the list of physics, there's only one that's in the opposite direction, and that's neutron gamma. So ideally, if you can combine this negative and a positive, so it would have been ideal to say epithermal neutron and neutron gamma, you should have very minimal porosity error due to any liquid change. So now you can be confident in your porosity measurement. The quad is actually built with thermal neutrons, and the reason we did that is because we use this error due to liquids for our saturation measurement. So we did want a better dynamic range, but still we used neutron gamma to give us the negative. And so I'm going to talk about these curves. If you remember quad total porosity, I showed the depth of investigation. This is one of our primary curves. It is probably our number one primary curve. It's based on 4 detector mathematics. It's based on neutron, neutron, neutron gamma. And it includes matrix porosity and clay content in this measurement. So I'm just going to show this. Maybe it's easy, maybe it's not. But if we look at neutron gamma porosity error due to different liquids, you can see it's in this direction. If you look at the neutron with the different liquids, it's in the opposite direction and it's quite large. If we use the correct combining formula, we can minimize the error due to liquids. we now do a calculation, which we call a quad liquid. Again, it's a 4-detector mathematics. In this particular mathematics, we're trying to exaggerate the liquid air. And so this curve, called quad liquid, is very sensitive to liquid changes. Again, if we look at the air and the neutron gamma and the air and the neutron, if we combine them this way, they actually have better dynamic range. So it's much more sensitive. The porosity air is much more exaggerated due to liquids. And I want to make a comment here. This is due to liquids. Gases will not, you will not see this effect with gas. There's one other curve. I'll just talk to it because I'm going to show you. We put a log together, and that's our dual detector neutron. This is just the ratio of the neutron detectors, similar to a CNL curve, or it's just the ratios. So we use this to identify gas and to help discriminate between light versus heavy oil. And very simply, here's the graph of the liquid effect of this curve. It's just the neutron. So that brings me to our little how we put the log together, just to give you an idea before I dive into examples. So let's assume we have a formation of shale and sitting on top of a sand. Let's also assume that the gamma ray represents the shale volume, and this is what it looks like. So typically on a quad log, we present our V shale or our gamma ray in track 1 on the left side. Now, let's go ahead and put some liquids in this rock. So if we take a bound water, put bound water in the shale, and we actually have the same salinity, the bound water is the same salinity as this fresh water sitting in this sand. And then we also have a saline water at the bottom of our sand, and then we have 40% oil saturation in this sand and 80% oil in this sand, and this is all relative to fresh water, and we put a gas cap. So here's all the scenarios that I can think of at the moment. So when we process the data, one of the first things we do is we calculate QTP. Once we're given our bit size, we go ahead and we put our QTP curve on. And you can see here that there is a shift in the porosity. I'm assuming that the sand is a fixed porosity, but it is a neutron device. There is a small effect due to gas, so it will be lower. We do a gas correction to take care of this, but just be aware there is a gas effect on the measurement. So the next curve we do is our relative bulk density, and this is the one I was telling you where we compare neutron versus gamma counts. And so we typically, normalize this in the sand. So if we use this chart division as our normalization point, you can see in the gas to the left is light density, and over here in the salt water, it's high bulk density. And so you can see the little shifts in this density measurement due to the liquids, the different liquids and materials in the pore space. Next, we go ahead and we put our quad liquid curve on. Now the quad liquid is set, the span of this curve is set by putting an input of water salinity and an oil API. With those two parameters, we fix the span, and then we put it on the log. Now, due to borehole effects, it's really frustrating, I think keeps moving. What we do is we actually shift the curve and we tie the relationship down in water. So our overlay is in a water sand if we can. So without knowing anything about the sand or where we are, we will tie at the bottom of the sand and assume it's water. And then what we do is this is what Andre does, he's a specialist. We look at the separation. So any separation to the right of that curve is an indicator of oil saturation. But when we tie at the bottom of the sand, we can see that we've got oil separation in the shale. We have oil separation everywhere. So our first assumption that this bottom sand is the water salinity throughout the sand is probably incorrect. Now, having nothing else to go off, we will probably end up tying in the shale for salinity. And if we tie up here, then you get an overlay relationship like this. And so you can see that we actually get quad liquid over top of QTP here, and quad liquid underneath. So anything underneath, we shade green as our hydrocarbon indicator. And then we also go ahead and we do our dual neutron. curve. So that's in the next track. And what we do is we tie this curve in the same area that the quad liquid curve was tied. And then we shade anything underneath red. So there's our process log. Now the interpretation begins. So we are in a situation which I would call red, black, and blue relationship, but you see we've got a red, black, blue relationship up here. So what we need to do is be able to differentiate, is this a gas zone or a salt water zone? And the nice thing about the gas, it's like bulk density. So we can look at the porosity drop, we can look at the relative bulk density and see that, okay, this is a gas response, this is salt water. So from here on in, now we got to calculate saturation, and the amount of separation is related to the amount of saturation. So the more separation we get from quad liquid to QTP, the higher your oil saturation. Which leads me to our saturation equation. So, like I said, we look at the separation from QT and quad liquid. So here in our equation, we have QTP minus quad liquid. So that's the amount of separation. We have a fluid coefficient, which tells us that for the given water salinity and the oil API, the maximum separation, which we have tables for, should be so much porosity unit separation. And if we only have half of that up top here, we would get 50% saturation. There is a formation factor, which Andre can talk to here because we've gone, that is just the inverse of porosity, right?
Yes.
So initially, when we started doing saturation and doing the research, we assumed there was a formation influence. We've since found out that that's not the case. And I'll show you some of the work we did at Total facility in France. But so basically, I'm going to call it a porosity independent saturation measurement. It's not entirely true. There is a small dependency, and I'll show that in some upcoming slides here. So here we go. We'll talk about it right now. So I'm not sure if you guys are familiar with this facility that Total built. It's a very new facility. It's in France. We were invited by Total to do measurements there. We've actually been asked to provide the quad Neutron so they can model their facility as well. And we're just in the process of trying to get that all lined up. And so at this facility, there's 22 rock standards for validating measurements for Total so that they can be more cost effective for their exploration. It cost us a fair bit of money to go there. It was almost 70 or 75. And I'll just show you an example of some of the data that Total compiled at the facility. So this is one of the silos, and it has two rock standards. One of the rock standards is this 30% porosity. The Total spared no expense. I mean, absolutely fantastic job. I give them full marks for making a standard and doing their best. And so here's an example of 10 days in doing our standards. One of the questions we always had is what's our formation factor, liquid and QTP? Well, when we actually plotted the data, so the black curve is our QTP and the red curve is our quad liquid. And that's from a porosity of less than 1% porosity up to 30-something% porosity is changes. And that's if we tie our quad liquid, here's where quad liquid went for 100,000 ppm salt water, and here's where it went for 200,000 ppm. So huge degrees of separation due to on the quad liquid curve. What's interesting to note is the slope we've added more capabilities here at the Roque facility. We've put a huge sand standard. How many barrels was that again? I can't remember.
Yeah, I don't know.
It's a huge, huge tank we've added, and using Total's data and our some extra data we've collected here, plus our modeling, and Mr. Andre has gone ahead and he's built some three-dimensional relationships here between quad total porosity and quad liquid. See, here's a three-dimensional relationship response chart for between quad liquid. As wellbore salinity changes and formation salinity changes, and then what is the response function? So we need to know these response functions to actually calculate saturation, but we now have charts for this. So here's another one. Here is salinity versus porosity. And you can see they behave very similar, which is what we've seen at Total. And this is the response function. These planes are built for 4.5-inch casing at 200 millimeter bits. Okay. And one last thing. So we have built a response chart for the quad neutron. Here it is. We can get Abdullah to maybe print some copies off for you guys and distribute it. So, but here is the response chart for the quad neutron. This particular response chart actually shows anything you'd like to add to that, or?
No, not really. I think there was a question what we received before before the meeting.
Yeah.
If we can differentiate gas saturation or.
Yeah, maybe to elaborate, you know, can we tell the difference between gas and a light oil? The quad is built on the liquid response. So a light oil is a liquid, the gas, as long as it's a dry gas, there's no problems differentiating the two. If we start getting into condensate
or amount of oil in the measuring volume. And so if you look on that from open hole perspectives, on open hole we have resistivity curve and separate, or based on that resistivity curve, you can tell if that's hydrocarbons or water. And in order to separate hydrocarbons between oil and gas, you need to use density or neutron, right? So for us, we measure oil saturation and gas saturation. These are two separate measurements. But the second thing here is production results, right? You can have one set of fluids in the formation, but depends on the pressure, surface pressure, and how low pressure goes down. So you really need to understand production data, and reservoir engineers or people who deals with reservoir can help you with this.
All right, I think. Let me just go back to that one. So I'm going to pause here for a second. We'll open it to questions. Let me add this before we dive into the questions. Is most people, when we present about quad neutron technology, I'll be honest with you, it takes about 5 presentations before people start to understand fairly clear on what the measurement is. So you know what? Feel free to ask questions. We're gonna email out a copy of the presentation to you guys. So feel free to send email questions down the road. We'll try and get them all addressed. Send them to Abdullah, and then we'll handle them.
And there's much like Herman said, there is much more behind it, behind that presentation. We didn't show any equations or didn't prove or didn't even try to prove what that works based on physics, based on equations. Supports our theory and measurement.
Yeah, and that's a good point, because one of the things too, there's limited time here. We got a pretty wide audience, so if people want to know more on the physics side, I'll let Abdullah organize maybe a physics presentation, or we can go through some of the mathematics if people need more of that. It's great if you have your own data sets to work with, but we can go through the theoretical side if that helps you. So I'll pause you for a second.
Yeah, I think there are questions in the chat box that we might need to, yeah. So there's a question here. How well does the tool perform in wells with potential interference from juries or downhole equipment like thick pipe sections and gravel packs? Then the same person is asking, can you also speak to any limitation of the tool?
you know, to do the processing and the interpretation of the quad neutron, we do overlays. And the advantage of doing overlays is it removes a lot of the common signals. So when we see jewelry or downhole equipment, as long as we have, let's say, a long enough section, if we start having little 1 meter chunks of heavy pipe followed by some stuff that's not the same and it goes back, we can do a rough interpretation, but our method uses an overlay. So we can actually get rid of changes in pipe. It's easy to see. I have an example. I think I have an example of a gravel pack coming up. Typically on jewelry, if you have a packer, the packer isn't big enough for us to look behind the packer, but hopefully you don't want to look behind the packer because that's where the packer is. So you'd have to move everything. So for the most part, interference from jewelry is not an issue as long as it's big enough. Blast joints, for example.
we work in blast joints, we work in gravel pack environments, and sometimes it's quite interesting to work with gravel pack because you can see the separation of the different material in the gravel pack, heavier material at the bottom and light at the top.
Yeah.
And we can see it on the log and create zones accordingly.
Yeah. And I see the second question here, speak to any limitations of the tool.
One of the inputs what we need to calculate saturation is oil properties.
Yes.
Oil API.
Oil API.
We have algorithm to predict water salinity where we overlay QTP and quad liquid. But for oil API, we need some kind of input from the customer.
Yeah, that is one limitation to do saturation. The other one again is maybe if there's the changes in the wellbore, the same like the jewelry, if there's small little sections of heavy changes, and it's more wellbore, it's not about the formation. That is a limitation. We need a decent length of non-changing environment to actually do the interpretation. I want to say that is wellbore changes. Is there anything else you can think of?
Yeah, not really. The beauty of the method is it is porosity independent, so we can differentiate gas from high bulk density stuff and what have you. So, and overlay techniques.
All right, there are a few more questions that we're getting.
More.
One of them is, does the tool differentiate between gas and oil, or is the differentiation done by interpretation? He's asking whether the two differentiate between gas and oil, or we have to do the differentiation by interpretation.
I think they all have to be done by interpretation. I mean, the curve responses are there. So the gas, I mean, it's easy to see the effect of gas on the detectors.
The problem is it could be gas or high bulk density material. So in order to differentiate high bulk density from gas, you need to process the data and look not just
at one measurement.
Yeah, on one measurement or how curve behaves, but put them together and see how they all behaves.
Yeah. Does that help?
Okay. Then another one. Okay. Another one from SCN Umoran is asking about fluid type differentiation. Do you require a known downhole environment, say known water bearing intervals to calibrate your quad liquid core? Do we require a known downhole environment, like a water bearing interval to calibrate quad liquid core?
You know what, it is, if it's available, it is very good to do because we have to make an assumption when we do our overlay. So if we make an assumption that it's 100% water-bearing sand, and it's not, sometimes what we see is that people don't truly know what water salinity they're dealing with. We do some calculations. Maybe the oil API is unknown, or there's a number of variables. So what we do sometimes is we can process for, here's, let's say, the median response, but we could say, well, here's a pessimistic interpretation and here's an optimistic interpretation. But at the end of the day, yeah, it would be handy to know where to tie that curve. If we know the water salinity, so if we are given water salinity correctly, then I don't need this water-bearing sand. I think we can go ahead and do an overlay. We'll see if there's an error in our overlay at that point.
Just a couple of things to add.
Yeah.
When we process and calibrate quad liquid, there are two intervals where, or two main zones where we can overlay the curves. First interval, like Herman said, we can use a water-filled sandstone, but the second environment will be shale. So as long as water salinity in the shale is the same like in the sand, we can use that shale to tie, or in most cases, we use the shale to tie QTP and quad liquid.
Yeah.
So yeah, it's nice to have some kind of water salinity from the customer, but we can back calculate that water salinity based on our measurement.
Is there another?
Okay.
Open to,
I think the other question, I think we have answered it relating to blast joints, jewelries that can attenuate the readings. There's a question around that, but I think you mentioned it. How does a core perform across zones that are perforated where there are blast joints or other jewelries? I guess you mentioned it there.
yeah, blast joints are long enough that we can actually retie everything and do our overlays successfully. So,
and I think one of the examples
coming up.
Yeah.
All right.
Okay, so I think you can go ahead with the case studies. There are no questions.
Okay. Yeah. All right, thanks. I'm not a Zoom professional, but I'll carry on here. Okay, so I'm going to show these some international case studies. So I'm going to look at more on how to optimize production. So before I dive into these case studies, what are the pains? You know, if any of you guys are production engineers, I'm sure you'll relate. So complex wellbore completions make it difficult to get good quality data in a cased-hole environment. Some measurements require open hole data inputs, which may not exist or be limited and or of poor quality, or it could be old. And then open hole logs are not current and may not represent the current situation. As I said, they could be just old. Someone made a comment to me, one of my customers said that, you know, if I give you open hole data from 30 years ago, it's like taking a picture of a beautiful girl 30 years ago and saying she's still beautiful today. Well, if it's your wife, that is the correct answer. So, but if she's the girlfriend, maybe not. Anyway, all right. Anyway, so, you know, having current data is always the best. This is the current situation. You don't want to have the doctor analyze your MRI from 30 years ago. You want the current measurements. So, so those are the pains. But how, you know, what does a quad neutron? Well, first of all, it's slim design. We got the dual physics. It's deep reading. So the environment, we can handle these complex environments, and we can get data. We don't need the open hole input either. So that's the advantage of, you know, using a quad neutron for looking at production optimization. So
and we provide the data like open hole.
It's right? Good quality data. Yeah,
open hole measurement through the case hole in the case hole environment.
Yeah, similar data set. So I'll just walk you through what a typical quad neutron log looks like. So when I look at these case studies, you have an idea. So on the far track, we always put our gamma rays. We have 2 gamma rays that we present. They're permeability indicators. I'm not going to go into that during this presentation. The next track we have here, we have a lithology track. This is our interpretation of lithology. And, you know, we get some people going, oh, that's not how I think it looks. Well, you know what, by all means, any input, if we work together to get the solution and improve production, it's always a better result. But we always put our interpretation down, and sometimes it sheds light to people if we do it independently. And so I'll just quickly on this one here. So, green is shale in this example, orange is silt, yellow is sand. We show any high bulk density indicators as a little blue shading in here. So there's some high bulk density material here. And so for the most part, it's just more, here's what we've identified. And this, if you remember in my little animation on how we make log, this is gray shade and we shade separation red. We also plot saturation. In this particular example, I have the open hole, the original open hole saturation. So you can see here was the original open hole saturation calculation, and the green is what we saw. So the open holes from 1980s, quads from 2012, some of the parameters we are aware of or we believe is 25 API oil and 8,000 ppm water. So this particular well, the customer had all this perforated. When we went to log it, the well was doing 277 tons per day of fluid, but only 7.4 tons of oil, mostly water. So 97% water cut. So once we logged this, we said, well, this looks like your lower zone is depleted. But the upper one almost looks like original saturation is still in place. Now, a lot of people say, oh, that's impossible. You know what? No, we see it all the time. It is possible to have open perfs for 30 years and not deplete zones. And it's all related to permeability. This lower sand is much better quality sand, and it just continually produces water. This upper sand won't do anything. So the customer went ahead and just simply squeezed these perforations off and put the well back on production to try to isolate this high perm sand. And when he did that, he dropped his fluids to 25 tons a day from 200 to 77 tons, but his oil went up to 11. So dropped the water by 95% and increased the oil by 49% simply by squeezing a set of perfs. No extra perfs, nothing. So this has been open for 30 years and now it's increased production. So that's a beautiful example of a true water shutoff. So this is how the logs put together. We'll dive into the next ones here. So here's another well. This is from the USA. This is an old well formation that they work on. And the customer went ahead and ran a carbon oxygen log. And based on carbon oxygen, they showed this lower zone to be almost 80, 90% oil. So the customer said, great, received 100% water. And then the customer had to make a decision to do something. So they went ahead and they targeted these two little blips, which are only 30% saturation, 40, and put that on production. And it was 87% water cut. It only lasted for 2 weeks and then went to 100% water. And that's when we showed up. We said, hey, so the customer went ahead and he squeezed off this set of perforations. He drilled out the plug and squeezed off this set of perforations, and we ran the quad log, quad Neutron. So we see fairly high oil saturation down in the lower interval, but we also see that we low permeability anyway. When we came up here, we see this is our next best zone up top here. And the customer said, okay, we're going to go ahead and do that. So they went ahead and perforated this upper interval and put it on production. And so they had 1.5% water cut. Now, this well before the quad was doing 260 barrels of water, 40 barrels of oil, and 36 equivalent gas. After they did all this work over and reperforated this upper zone, and 110 gas equivalent. So, and this well, to my knowledge, has been going for years. It's gone for a long time. So customers, this is a very excellent result with this client. I know these amounts that you're looking at are so here's an example of, I believe this is a gravel pack. When we ran the log, we can tell by the quad log that this lower zone is 100% water saturation, and it's the zone of highest production. We can tell that from number of things. First of all, the porosity is crazy in here. I think it's a sand screen is what it is, or gravel packed sand, and they have huge porosity, big washouts behind this thing. And then we can also see by the gamma that there's lots of norm contamination through production. And now I know it's a sand, but this is the only way we're going to flag this scenario. So, and I told the customer, I said, well, the tool did not quit in this sand. It worked great for this sand, and this sand. It didn't decide to quit. It's saying that there's a high amount of clay. And I said, and the clay is affected by aluminum presence. So I said, is it possible that the sand has maybe aluminum mixed in there? And they said, no, it's all the same. And I said, well, somehow I think aluminum got in here. And I said, well, my interpretation is that it's drilling mud invaded. And they were reluctant to even consider that. And I said, well, and I said, and the other thing I see is I see gas presence. So there is gas. It's interpreted as a water sand. And I said, why is it interpreted as a water sand? You have neutron density crossover from open hole. And the only reason they interpret that as a water sand is because the resistivity was low. I said, well, probably the neutron density is still sensitive to the gas. And the mud invasion will just short circuit the resistivity measurement. So anyway, my interpretation in this sand is a mud invaded sand, and I'm pretty confident in that interpretation. They said, well, we still don't like it because your porosity is wrong here. So up in this interval, they said, well, you show it almost goes to zero. I said, okay, but what I also see in the middle of the sand is deep cement or a high calcite stringer. And I said, I believe it's cement invasion. And there was a question, why was there no cement invasion here? I said, the reason it can't invade is because there's drilling mud in the way. This zone, if you look at how the sand is, just on gamma ray, for example, this is a very clean sand. This is a dirtier sand, so it has lower perm. It's probably low enough perm that the mud doesn't want to invade it, but the cement invaded it. It's probably a higher density fluid, so it invaded this system quite easily. And if we look at the neutron density crossover, it was a low pressure gas sand, so not a lot of resistance. So anyway, I love this example. It's I find a mud invaded interval and a cement invaded interval all within stacked sands. It's beautiful. Anyway, customer went ahead and perforated the lower interval, which we said looks like laminated fingers of cement invasion, and she got a mix of gas and water, and that's exactly what they got. So they were happy with this. I'm going to show this example. 42 barrels of oil on 3 wells. It was a project we did down in Texas to rework some very old wells, 1972, I think the oldest is in the 50s. But we worked in combination with Blue Spark just on this well. And the problem that Blue Spark was having with customers is that they want to perforate, or they want to re-stimulate everything. So here's all the perforations in this particular well. And so what we said is, why don't we optimize the stimulation program to oil-rich intervals? And so by running the quad, we can identify oil, like high oil saturation intervals. We can identify low oil or mostly water saturated intervals across the perfs. And then we can also identify low perm areas too and say, well, you could try to stimulate this, but it might not come in. Try to avoid stimulating these type of intervals. Stimulate oil preferentially. And so by doing that on this project, the customer was able to actually decrease some water flow and increase oil production. It's not a lot, 104 barrels in 3 wells, but anyway, it's just an example of how you can use the tool in old well bores to optimize your stimulation programs as well. And I like this one. This is a beautiful example. This is a South American example. The customer, this is back when the oil price crashed in 2015 and they needed to increase production. This well went to zero. All production stopped and they needed to increase production as cheaply as possible. Now, they wanted to log for bypass pay, but they had a packer and tubing in the hole, and the cost of pulling that out was a bit prohibitive. And they were looking at pulse neutron, and they were asked by the service company to pull that hardware out to do the measurement. we told them just leave the hardware in and we'll just do the measurement through the hardware. And when we were finished, we identified this little sand up here that looked very oil rich. And so the customer went ahead and just perforated through the tubing and the casing, which, okay, I don't recommend that, but anyway, that's what they did. But I can't complain about the results. So before they had no production, after they had 74 barrels of water, 1,400 barrels of oil production, only perforating through tubing and the casing. So pretty impressive result for this one. Anyway, those are, I believe, most of my international examples. I'm going to pass control here, at least I'm going to try.
I think there was a question.
Oh, yeah. Is there a question? Yeah, we can pause here for a question, sure.
Yeah, we have a question there. So asking if in a scenario of a water flood, feed underwater flood, where salinity is varying or known, how do you infer fluid types?
Oh, that's a good question. We do a fair bit of water flood intervals. And so what we can do is and this is a great place where you can actually make this tie on the liquid curve and say, well, I'm going to make an assumption that we're tied here. And if you remember in my little animation where I made the assumption at the bottom of the sand and I tied and I said, oh, everything looks like oil. That assumption is incorrect. So we can qualify our assumptions, or at least say, hey, that assumption looks to be incorrect. In water floods with mixed water salinities, it's rather impressive. What we can do is we can tie under an assumption of a water tie, and then we can see the salinity changes as the quad liquid curve goes over top of quad liquid. So the further it goes over quad total porosity, the higher the salinity. So we can actually do a salinity graph, a salinity plot. And it's very difficult when you got mixed waters and water salinity. So what we can do is we work with, typically we work with the client and go, well, here under this assumption is what we see. And so we can work with them and they say, well, let's make an assumption that it's this, or we can make it more pessimistic, make it more optimistic to see what the scenario looks like. And at the end of the day, the oil zones are still going to be the oil zones. So it's just a matter of, can we optimize? Typically we do a lot of horizontal water floods, so they're quite big, but you can isolate different sections quite easily and improve your production. So hopefully that answered the question. Any comment on?
Yeah, we can look at the other overlays too. Some overlays or some curves will be affected by light hydrocarbon presence, like we shale based on quad clay. So if there is a light hydrocarbons we're working with, if it's not a heavy oil but something like 30 API oil, then we can incorporate other overlays to confirm our assumptions.
Assumptions. Yeah. Okay, good answer. Okay, I'm going to pass this over to Abdullah. I'm going to let Abdullah present these Niger's case studies too. All right, Abdullah, I believe it's under your control. I'm going to mute my microphone.
Okay, thank you, Herman. So just to run through the Niger Delta case studies. I think we have to take it. All right. So this is one of the case studies in Niger Delta, where we have the client's objective was to actually identify present gas oil contact and present oil water contact. And as we can see, we ran quad and we're able to see that the oil water contact, the current one, has moved by 18 feet. Like Herman said, we normally overlay the quad liquid and the quad total porosity. And when we have the separation, we have oil where we have it tied in. most likely is water or maybe in a shale environment. So we could see also the GOC, clearly delineated by quad log. So I'm just going to run a bit fast because of our time. To the next slide. Trying to control it from here, Aman. It's a bit. Okay, so this particular one here was a very, very interesting case where the client actually needed to make a decision. It was a well with little or no open hole, a newly drilled well. Because it was high angle, they could not run the typical neutron density log. So they had only resistivity log. And they needed to know the current GOC because they have only one well in that field. And of course, to know where to perforate on the OWC side as well. So we ran quad. And as you can see, we were able to delineate properly the GOC. And the client perforated based on quad log. And the well came up with almost 8,000 barrels. So an SP paper was published for this particular well this year. We did this together with New Cross. There is an SP paper on it, and it was one of the major successes that Quad has recorded in Niger Delta. Limited open hole data, no neutron, no density log. It was Quad, and we were able to see clearly where the GOC and the OWC was. And we were able to also get about 30-foot pay extra that was missed on the resistivity log for the client, which was really, really impressive. And the last one I'm going to talk about on the case study is where the client, they had actually I think I missed this again. Aman, I think I missed the, all right, there's it. So where the clients, actually, they had this well producing for some time, but they just told us, okay, can you help us check the current saturation? So we went in, we ran quad, and as you can see, we actually identified for the client a missed pay because on their log, they have used a gamma ray to do their lithology calibration. So we told them that from what we could see from the clay curve, quad clay, we could see that about 15 feet of pay was actually here because this zone was actually radioactive sand, so it suppressed the gamma ray. And Quad was able to properly show that this zone was even oil field. It was after we presented this result that the client told us that actually they noticed that they produce actually more than the reserve booked for this well, as they can, even the stock, not even the reserve, the stock, they produce more than the stock. So, and this actually gave them insight to further do some work to see how extensive the reservoir is. So back to you, Aman. I think this is the last case study here. But I could see a question. Okay. Someone is asking, I can't see the OWC in your XP example. Okay, maybe that was the part that we wanted to emphasize the GOC. That was why we didn't put it. But we'll send right away the SP paper number on to all the attendees so that we can check it out. We have SP paper number for this particular case study of the SP example I gave so that you can check it out. Yeah. So back to you, Aman.
All right, thanks, Abdullah. So I'm just going to quickly talk about some new developments, and then we'll be wrapped up here. So just so everyone knows, like we've been working on a prototype spectral quad neutron tool for quite some time. We actually have built the prototype. We've been testing it for probably 2 months. So we're just in the process of collecting all the spectral gamma data more from a lab perspective. Should be entering field trials probably within a month. And by adding spectral capabilities, it'll give us some more insight and give us more diagnostic abilities for the quad neutron. So this is going to be exciting to collect all that spectral energy. We're also testing a prototype spinner tool that we are looking to add to the quad neutron, again, to make the quad neutron more of a one-run diagnostic tool for production optimization. And then the other thing we're working on, I mean, we're working a lot, but the other one I want to mention is automating our quad modeling software. So we've been working on this building quad modeling software for quite some time. We're going to be working with Total, helping them with their modeling as well. And our goal is to enable faster client scenario modeling. So if there is a particular scenario that somebody says, hey, can you give me what the model would show? We can go ahead and at least put that out for you guys. So that's pretty well it. The summary, hopefully you walk away knowing that the quad neutron is not just a neutron tool. It's amazing how many people think that, but it's not. We utilize two physics, neutron, and neutron gamma, and we combine them. That gives us a deeper depth of investigation and the ability to do standalone measurements. So with that, I want to thank everyone for their patience. Oh, if there's any questions, was there another question? Sorry, okay, before we exit, questions.
Yeah, I think we have one question here. Do you have Niger Delta examples, cross-special completions, such as blast joints? Yes, we do. We have Niger Delta examples with gravel packs.
Is a blast joint.
Blast joints. Yeah.
So, okay, Andre says there's a blast joint in this one.
Yeah, there is a
yes
two red lines.
Oh yes, yeah, these two. This is the blast joint here.
Yeah.
So this interpretation was done across the blast joint. Yeah.
And the previous well, I believe, had a blast joint. Yeah.
Yes.
One more.
No, this is no, this is in casing.
This one. Yeah.
This one. Yeah, blast joint.
So that's double completion, double string completion, two tubings, right? And blast joint.
Yeah, there's blast joint here, the green one, right?
Yeah.
That's correct.
So yeah, we do have some. Yeah. Is there any question related to that?
Okay, I think Mr. Tunji Olukalde, I think maybe he wants to have, is one of the participants. He has the feedback or question also. I mean, feedback or comment.
Okay, I'll mute.
I don't know whether it's still on. Okay. Mr. Tunji, you can go ahead.
Yeah, so thank you for the opportunity to add my testimony to the performance of the quad neutron. I've had the blessing of using it across difficult situations. In fact, everything that's been said about it, the tool has proven itself. From running blind without any data, just on its own, and coming up with correct results, to also helping to prevent premature decisions being made. There's one particular example where the field development was earmarked to go ahead, and there were concerns about the saturations. So fortunately, there were 2 wells in the field that had quad deployed in them. And rather more by accident than design, the interval in question was locked with quad. And lo and behold, the indication of saturation that was expected was not borne out by the quad information. So upon closer analysis of the of the open hole data, it became evident that two things, either you have incomplete charging or something has breached the trap, and consequently, what you have there is more like residual or incompletely charged formation. And so rather than go ahead to start developing, the appropriate decision was to acquire additional data, piggybacking on a well going to a deeper reservoir, which will cost less than $500,000, as opposed to going to spend in excess of $15 million for a well to develop that particular site. So that's one example of where quad added value unintentionally, just because it went past a reservoir that was not targeted for logging. So one thing I've noticed with people is they tend to run the quad across specific intervals. I wouldn't advise that as best practice. Like it was mentioned earlier on, quad doesn't need a water leg for calibration if you could provide the formation salinity you've measured from produced water or water samples. However, when you log multiple reservoirs in one go that are stacked together, you can see that quad responds to trends more accurately than a lot of tools. So the trend can help you reduce the uncertainty, tighten the envelope of your interpretation, and you can more confidently make decisions regarding completion. The other aspect of quad that is not being utilized, and which has proven itself in two cases that I know of, is the silts, the fines, the mud invasion. In two cases now, it has indicated, oh, there's problem here, try and stimulate or remediate before you complete. And in both cases, the operators have gone ahead to complete without hitting the quad warnings. Subsequently, when they try to put the wells on stream, no show, okay? The wells will not flow. And running a BHP surveys showed, intermittent production, but the buildup was so slow that with a skin in excess of 10 in one case, in excess of 20 in another case, positive skin, that they now realize that what the quad was indicating was correct, and follow-up remedial actions became more expensive. What could have been done with a rig within in less than 2 days has taken weeks to plan and several days to implement in order to get those wells flowing. There are other advantages to the quad that people don't say. There is the borehole resistivity measurements curve, which is in the track in front of us. I think it's the blue curve, okay? In one example, where we ran it in a static well, it was able to show the segregation of fluid in the well. It's categorically stated that, interpreted properly, that the well had not fully unloaded, and that was what was inhibiting the flow rate, okay? The brine was too heavy for the well pressure to unload naturally, so it needed help. And the quad tool was able to pick out this, and when combined with the static pressure survey, everywhere the BRM indicated a change in fluid nature, the BHP survey indicated a fluid contact. So going from gas to oil to water plus oil mixture, and then to heavy brine at the very base all the way to the top perforations. So there are many advantages of this tool, and we're just getting there, to use it.
Thanks a lot. Thanks so much, Mr. Tunji. There are two more questions here before we go that someone asked. From Ms. Ifa in Ophia, given the interesting result from repeat logging, will you recommend some sort of 4D logging for identification of bypass pay. How useful is the tool for electrolysis in terms of better definition of the quality of the intercalated sand shale units? So maybe you can, Amon, you want to look at that? Then there is another one after that, but you can take this first. Yeah.
Okay. Yeah, I mean, anytime you can do time-lapse measurements, it does certainly shed light on what the reservoir is doing. And it also, you know, with the advantage of time, it's like any decision you've made in your life. You say, wow, if I'd have known what I know now, I might have changed my mind. So yeah, for sure, any time a time lapse, especially if you're responsible for production optimizations, and if, or a reservoir engineer trying to see how is this reservoir behaving, for sure the 4D measurements are optimal for that. They're excellent for that. And you know, you can also validate your initial assumptions. You can improve them. You can also do that by doing a number of wells. Sometimes we get one well for a client and say, oh, we want to try it on one well in a field that we have no experience with. And, you know, it's tough to make one assumption on one well. And as Mr. Tunji was mentioning, to have the ability to do two wells in a field. By having those two wells, at least now you can check your assumption that you made on the first well. Does it hold for the second well? Same with the 4D. You get better at your interpretation. So we're trying to get better. So anyways, there's another question.
Yeah, the one on the electrolytics, the performance of the tool, which I can testify to is very good. It will resolve according to its vertical resolution, but the tool is not fooled by thin beds. Like the example shown by Herman earlier on. Yeah. Oh, actually, this one. Yeah, that's it. This particular one. You could see that it picked up the extra pay at the top of the reservoir, and this is very, very common in Niger Delta, which was ignored because the gamma ray was high, and possibly the density neutron was not behaving properly. Bear in mind that this tool measures between 24 to 36 inches of rock volume in radius. So that's a lot of rock volume, and based on that, the signals or the data acquired represents an average over that volume, and volumetrically things are partitioned so that if there is any pay within a thinly bedded zone, you will see it. And that's a typical example in front of you here. And I've just come off a project where similar things exist. Hopefully they get to log the quad in those wells to verify those things. Indications were there on density neutron, but I think the quad will do a much better job. Thin beds, no problem for the quad. Or laminated formation, no problem for the quad at all.
Thank you, Mr. Tunji, for that. There is one last question. It said, from Mr. James. He said, can one identify the respective fluid types or contacts from the logs before its processing? Or Andra, yeah.
Before processing.
I think he's talking about the four field calls that come from the tool for this.
Okay.
Well,
yeah, with experience, you can look at those four singles and understand the relationships of them and make an interpretation. But again, it takes a lot of experience. I'm comfortable Andre could do it. He'd probably rather not. He'd rather do the math and put them together and look at the computed curves.
No.
No?
No raw curves.
No curves. Yeah, okay, it just counts. But no, you know what? So some of the zones are very easy. Like if you hit a gas cap, for example, the way the curves behave, I know if I'm looking at the data, the raw data, I can tell right away we've hit gas zone. Can we see oil water contacts on the singles? you'd have to look at all the data. You'd have to look at your gamma ray. You'd have to question, was it lithology? You also, if you see a change in the single responses, you have to question whether it was hardware related or wellbore related. You would have to look, as Mr. Tunji said, would have to look at your BRM curve. I saw it, at the end of the day, you can do it, but it's probably a little bit more robust to go ahead and calculate, just put the curve calculations together and just see what they look like.
And we usually provide raw data anyway. So if you want to play with raw data and figure out new processing technologies, then more than welcome.
Yeah, I think it's best to wait for the peripheracist to come up with results, to process and come up with results. Probably because if you recall the physics being presented to you, two physics are being combined. There are several things to consider, and you don't want to take a decision in a hurry that you might regret. But what I like about this tool is that the turnaround time between logging, between running in whole and getting your first pass results is very fast. Within 24 hours, you've got your information, or even 12 hours from pulling out of whole. So I would rather wait for the computing center to come back with the interpretation, especially if it's critical. So far, I've not had I've not had to wait on them, to make decisions so far.
Thank you, Mr. Tilly. So just a last one here before we call it a day. So this person is saying, must the data be processed by the contractor? I think we do the processing, but we also give you the raw, the last file that you can work with. Andre, you want to speak to that?
Yep. Yeah. No, that's true. You can get the raw data from in the field, or we can provide it after the interpretation.
All right. So Herman, is there any other thing from your side before we?
No, I just want to thank everyone for their time. There's a slide here with some references if you guys if you want to read some more. But aside from that, thank you to everyone for bearing with us.
Yeah, thank you very much.
Thank you.
Thank you for the feedback, Mr. Tunji. Thank you for the feedback. It's good to hear the customer perspective on our tool. So that's awesome.
Yeah. Thank you, everyone, for your time. We appreciate you so much. We look forward to working more with you, bringing what Quad could do to your own assets and helping you, getting more value from your asset. Thank you. Bye.